So the objective of this class is to determine the velocity and acceleration of a rigid body undergoing general plane motion using an absolute motion analysis. In previous class, we have studied that a rigid body can have three different types of motion: pure translation or curvilinear translation. Second one is pure rotation. And third one is general plane motion, which is combination of translation and rotation. So this topic is applicable to the motion, which is general plane motion, where rigid body contains different elements, and some of these elements have translation motion while the other elements have rotational motion. And how can we establish relation between translation and rotation, and how can we determine the velocity and acceleration? And that's the topic of today's lecture. So let's start with the reading quiz. So the first question is: a body subjected to general plane motion undergoes A. Translation, B. Rotation, C. Simultaneous translation and rotation, and D. Out of plane movement. And the correct answer, as you know, is simultaneous translation and rotation, because it's a general plane motion. Second question: in general plane motion, if the rigid body is represented by a slab, then the slab rotates A. about an axis perpendicular to the plane, B. about an axis parallel to the plane, C. about an axis lying in the plane, or D. none of the above. We have discussed this in the beginning of chapter 16, that general plane motion means the body rotates in plane, and the axis of rotation is perpendicular to the plane. So the correct answer for this question is about an axis perpendicular to the plane. So let's look at this example. This is a mining truck, which is a rigid body. It contains different elements, but we focus mainly on two elements. One of them is hydraulic cylinders. Again, you can follow my cursor. That hydraulic cylinders have translation motion when this cylinder extends. And the second element is this big bin, which has rotary motion when the cylinder extends. So during the design of the truck, engineers need to establish the relation between the velocity of the hydraulic cylinder with the rotational velocity of the bin. And similarly, acceleration of hydraulic cylinder extension should be related with the angular acceleration of the bin. So how do they do it? So let's study that. It's similar example. So in order to do such thing, they need to establish the coordinate system. So let's say this point B is a fixed point which is present uh, both on the cylinder which is extending, and it's also attached with the bin through this hydraulic cylinder. So the first step is we need to define the position variable S. So S represents the extension of the hydraulic cylinder. Because cylinder has linear motion, we use linear position variable S. Now with reference to point A and this link AB, we define the angular position of the bin using angle theta. So the next step is we need to write down an equation which can relate position variable S in terms of the angular motion of the bin theta. So we need to find out S as a function of theta. Once we have that function, we can take the first derivative of that function that will relate the velocity of cylinder with the angular velocity of the bin. And when we take the second derivative of the position function, you know that we get acceleration of cylinder that will be related with the angular acceleration of the bin. Okay. So as a part of the design process for the truck, an engineer had to relate the velocity at which the hydraulic cylinder extends and the resulting angular velocity of the bin. This is another application example where this is a large window. It's heavy that we cannot open it manually. That's why we need a hydraulic cylinder. In fact, the hydraulic cylinders can generate the forces which are very difficult to produce by other means, such as mechanical. So the large window is opened using a hydraulic cylinder AB. The position B of the hydraulic cylinder rod is related to the angular position theta of the window. So you can see that the position of the hydraulic cylinder S is defined here, and the angular position of the window is defined using the angular variable theta. So using the given dimensions, we can relate the position variable S with the angular velocity, with the angular position theta. A designer has to relate the translation velocity at B of the hydraulic cylinder and the angular velocity and acceleration of the window. How would you go about how would you go about the task? This is third application example. This is, let's consider that this is a piston cylinder engine, or you can say this is an internal combustion engine, or the slider crank mechanism. So in this example, this rotating link here, we call it crank. This sliding box, we call it slider or piston. And this connecting rod is in between the crank and the slider and piston. The piston travels the maximum distance from one point to the other point, and that maximum distance we call it stroke. For efficient design of the engine, it's necessary for the engineers to find out the relation between the linear velocity of the piston with the angular velocity of the crank. And similarly, linear acceleration of the piston should be related with the angular acceleration of the crank. And this slide explains how do they do it. So with respect to fixed point A, the angular position of the link AB is defined using angle theta, and the position of the slider is defined using a variable x. Now, using the link length as dimensions AB and BC, we can figure out the relation between x and theta. So once we have that equation, then first derivative differentiating x with respect to time gives the velocity of the piston that will be related with the angular velocity omega of the crank. And similarly, we can also relate the angular acceleration with the linear acceleration. So as I have mentioned in the previous example with the same window figure, that we need to determine the function S, which is for linear position of the hydraulic cylinder in terms of angular position of the window theta. And then next step is we need to take the first and second derivative of this position to get velocity and acceleration respectively. But be careful when you take the derivative that the derivative is with respect to time. So if you have theta in your equation, you also need to take the derivative of theta with respect to time, such as d theta by dt. So this slide explains the procedure for absolute motion analysis. The velocity and acceleration of a point undergoing a rectilinear motion can be related to the angular velocity and angular acceleration of a line contained within a body using the following procedure. So the first step is we need to define a point on the body using the position coordinate s, which is measured from a fixed origin, as explained in the previous examples. From a fixed reference line, we need to measure the angular position theta of the line lying on the body. And then using the given dimensions, we need to relate s to theta. That means we need to define the position as a function of theta. Once we have this function, we are almost done, because then the next two steps are take the first derivative of this function to get velocity, which relates to omega, and take the second derivative of this function, and we can find out the equation that relates acceleration a with angular acceleration alpha. In all these examples, we have talked about general plane motion because one of the body has linear translation and the second one has rotational motion. So this as a rigid body, the single window is undergoing both translation and rotation, so it's general plane motion. And this is absolute motion analysis because we define everything with respect to a fixed point, not related to something that's moving. That's why it's absolute motion analysis. In our next topic, that is section 16.5, we will talk about relative motion analysis. So we will define the position, velocity, and acceleration with respect to a link that is already in motion. Okay, so I would like to walk you through this example before we do in-class exercise. So in this example, link AB is rotating clockwise direction. At the instant, angle theta is 60 degrees. The sliding rod is moving to the left with linear acceleration of 2 meters per second square and linear velocity of 5 meters per second. What we need to do is determine the angular velocity and angular acceleration of link AB. So this is a slider, modified version of slider crank mechanism, where link AB is crank and this big rod, slotted rod, you can consider that as a slider. So this big link only slides left and right while this link rotates through 360 degrees. So at any particular position, let's say at theta equal to 60 degrees for this link AB, we know the velocity and acceleration of this sliding rod. We need to determine what are the angular velocity and angular acceleration of link AB in that situation. So what's our plan? So we need to define the coordinate system, and we need to define, because this is only one dimensional problem, such that the sliding rod moves only along x, not along y. We will use only position coordinate x that will define the position of the slotted rod with respect to the point A. And we relate that variable x with this angle theta. So we define x in terms of as a function of theta, and then we will take the first and second derivative of that x to find out the angular velocity and angular acceleration of link AB in terms of the linear velocity and linear acceleration of the slotted rod. We will use this notation often now onwards. So when let's say we have a linear position variable is x, then the first derivative of x, like the derivative of the position variable, gives us velocity. So velocity is dx by dt. We often write this as x dot. So the first dot on top of x represents its first derivative with respect to time. Similarly, two dots on x represent second derivative of x with respect to time, which is acceleration. So when you see x, x dot, and x double dot, consider that this is position, velocity, and acceleration. And x is for linear motion, and similarly when an object has rotational motion, we use position variable theta for position. Then theta dot, which is d theta by dt, is omega, angular velocity, and theta double dot, which is d square theta divided by dt square, is alpha, that is angular acceleration. So just remember x, x dot, x double dot, and theta, theta dot, theta double dot. Okay, so position variable and acceleration for linear and rotational system. So now let's look at the solution. So we define this point over here as our reference point. With respect to that point, we define the position of the slotted link using variable x. With reference to the horizontal line, we define the position of link, the angular position of the link using angle theta. We consider that anything that's going right is positive. That means the velocity and acceleration of the slotted rod are towards left, so they are negative. So first step is we need to now we have defined the x and theta, and we know the length of the link is 200 millimeter, which is 0.2 meters. Using this information, we can find the function for x in terms of theta, and that function is 0.2 cosine theta is x. So x is equal to 0.2 cosine theta, and the unit is meters. So once we have this function, it relates the position variable x with theta. Now when we take the first derivative, we will relate velocity with angular velocity omega, and when we take the second derivative, we will relate linear acceleration with angular acceleration alpha. So we need to take the time derivative of the position to find the velocity and acceleration. So derivative of x is x dot, derivative of 0.2 is like 0.2 is in multiplication, so it stays as it is. Derivative of cosine theta is minus sine theta, but be careful that theta is also function of time. So derivative of theta itself is theta dot. That's why we have to multiply it. And when we take the second derivative, we need to apply the chain rule, because now we have sine theta and theta dot, they both are function of time. So we have to first take the derivative of, let's say, sine theta only. At that time we keep theta dot constant, and second time we take the derivative of theta dot and we keep the sine theta constant. So this is x double dot. And again, we apply chain rule here while we go from x dot to x double dot. So once we have, so now we have position, velocity, and acceleration defined in terms of angular position, omega, and theta double dot is alpha. And now in these two equations, we can substitute the given values of phi and 2 for x dot and x double dot, because x dot is velocity, which is phi, but we will substitute minus phi because anything going right is positive for us. Similarly, acceleration is 2, but we'll substitute minus 2 because it's going left. And we also know the angle it's given in the problem is 60 degrees. So with this given information, once we substitute it, we can calculate theta dot from the equation of x dot, and theta dot is omega, and this is 28.9 radians per second, and it's going counterclockwise. And you can see that from the figure as well, that is indicated to go counterclockwise. And similarly, you can calculate angular acceleration theta double dot, and you will get the number negative. That means it goes clockwise, 478 radian per second square. In other words, we can say that when this slotted rod moves towards left, link AB angular velocity is clockwise, but angular acceleration is negative. That means it slows down as the rod moves from left to right. Okay, because as we know that angular acceleration is negative means something is slowing down from rotation. If it is positive, then it's speeding up, or its angular speed increases.